on a record. So first of all, for today, we'll discuss some theory, control theory, to be ready to start modeling in MATLAB. First of all, very shortly, briefly, we'll go through all the basic elements. All the basic elements. Okay. For control theory. And the first one is an integrator. Here we could see a small scheme in MATLAB.
Okay.
That represents this integrator. Yes, here we could see 3 blocks with a different coefficient of 0.2, 0.5, and 1. And initial signal. For the time moment 0, input signal is 0, and at the time moment 1 second, this step signal generator switch on the value of 1. Here we could see the black one is an input signal. Yes, it was 0 at the time moment 1, it becomes a 1. No, like an 0, 1, like it is the digital signal. And here we could see what will happen with this signal if we use an integrator with a different coefficient. So k is equal 0.2, 0.5, and 1. And here we could see the difference, yes? So, as we understand, this integrator, paint, I'll use maybe paint. Increase its value based on a k coefficient value, yeah, if we got an input signal. So if we want to represent what is going on, for example, let's use pulse width modulation. Okay, I want it to be black. Pulse width modulation, PWM signal, PWM signal, something like this. It's time. It's a signal. Okay, what will be? It's an input signal for an integrator. What we will got? Okay, let's use this. If we don't have a signal, it means that, oh, sorry, let's use this one to separate pulses. Okay, now we could use, so we don't have a signal, nothing is happening. We got a signal based on this coefficient, yes, as it is represented here, yes. We got an output signal. Now we don't have a signal, it means nothing is happening. We got signal, okay. I forgot, okay. Nothing is happening. We got signal, nothing is happening. This is how an integrator operates. So based on this coefficient, we got this angle. Okay, this is an integrator. Okay, let's go next. The next one is an aperiodical transformation. So the same input signal, a step generator. At the beginning, it is equal to 0. At the time moment 1 second, it will be 1. And here we could see the aperiodical block with a different coefficient, 1, 0.1, 2, yeah. And what here could we see, yeah? If this coefficient is very small, it means that the output signal, this one, tries to represent the input signal and goes very fast, yes, because we with this small coefficient, we decrease the impact of this block. As a result, it is at a very small amount of time reaches the input signal value. The idea of a periodical block is to represent the input signal. The main idea is the trip, yes, how we the trip, how fast and what will be the trip of this output signal. So the higher we got this coefficient, yes, the more aperiodical signal we will got, yes. So if we see the red curve, we could see that it will reach the input signal, but in a time of, it looks like 8 or 10 seconds, yes. So whatever happened, the periodical block will make the output signal similar to input in signal with a time delay and the trip like an aperiodical. The next one is oscillation. It is very similar to a periodical, but it represents the higher okay, I forgot how it is in English, this one. Second stage, or how it was, I forgot.
Square.
Square, yes, square. Yeah, sure. It's the evening, I'm just tired. Yeah. So that's why if this coefficient is very small, so it looks like a periodical. But when this coefficient is higher, it means that the square part have a bigger impact, and we could see these oscillations or fluctuations, yes. But the main idea that at the end, the output signal will be equal to the input signal. This is the oscillator. The next one, okay, this is the time delay. This is very simple time delay. So it represents the input signal only with a delay. So it is very simple time delay. And the next one is a real differential one. We got the differential and in real differential and real integrator. What is the difference? Why we separate integrator and real integrator? Because as we could see from here, when we talk about the just an integrator, we could see this here a surge, yes, like a jump, a surge of an output signal. But in real life, we have an inertia, and every process in real life can't happen like a surge. So in this way, we're going to see, no, it's okay. The real integrator looks like this one, real integrator. Then this rise of output signal goes not like a straight line, yes, but at the beginning it goes like an aperiodical. This way we separate an integrator and a real integrator. Yeah, the same is for a differential. We got a real differential and just differential. Yes, when we for example, for this, when you see the case, this is a real differential 0.1, yes, so it means that it represents the input signal. Yes, the impact is very small, but we see that it is the same like in like an input signal, not at the moment, but with a little delay and this periodical part, yes. And here we could see with the higher coefficient, we have a higher impact of this differential block. We could see that we have a difference in a phase and different in amplitude. Yes, here we could see. But with the main idea, when the output signal will be the same as input signal, they will be the same. So these are the main blocks for a control theory. I think you should know them. And now let's go to the schemes. Okay, let's go to the schemes in MATLAB. I'll send you these schemes.
Okay.
Because this will be your homework.
Okay.
And now we'll discuss about what we see here and what should you do. But I think I need to come back. For example, here. Do I have? Wait a minute. This is. I think I need this one. I think I need this one for you. Let's check. Oh. Okay. Yes, I think I need this one for you. Okay. Yellow, and this is blue. Okay, yes, this you will got this document for the analysis. So you will get the scheme and you will get this print screen, and your task will be to describe what is going on here and what parameter impacts to the result, what we see. Here we could see only the frequency. Here we could see this is a feature of frequency. Here you could see the 50 hertz, but I'll describe what's going on. So, oh, sorry, let's come back to scheme. Okay, so here we go. MATLAB, please come. Okay, so we have two schemes. They are equal, with idea to see the difference, and we use only this last one, scope, yes, to see the frequency.
Okay.
So we're interested in only in the frequency, what is going on. Let's play. Oh, let's press run to play the model. Okay, I need a little bit to run. Okay, it is ready. And here we could, what we got here, we could see, yes, we could see here only the blue line because they are equal. So it means there are two lines. For the first, it's a yellow, and for the second, it's a blue one. Yeah, but
Yeah.
they're equal. That's why we see the only one. What we see here, we have this. We see the frequency of 50 hertz. It's a nominal operation mode. When we see at the time moment of 5 seconds, something happened. And here we could see the deficit. Yep, frequency decrease. Yes. And after that, here we see the operation of regulators, with the idea that all the power generators gives more power based on the static coefficient. And here what we got, yeah, after the regulation. Okay, I can switch on. And what we could see here, here we could see the scheme from our book. Okay, in different words, this scheme represents the hydro concentrated power generator. So it means the one generator over all the generators. Okay, this power system is represented only by hydropower generators, yes? And how it is represented? This one is for the turbine. This block represents a turbine. This block represents the valve. Yep, valve that controls the amount of water to the turbine. Yes, and this one represents this static, this regulation for the generator that we discussed previously, the reaction of the generator to the frequency fluctuation. That's why we have this connection. Yes, here we could measure the frequency. Here we could see the result. Yes, here is input power. This one is a load reaction to the frequency deviation. And this one is load deviation. So in this case, what is going on? Here is a system, power system. Power system is represented by one parameter, this Tj. This is an inertia. So we could press here and we could see the inertia that is in seconds. Yes. So 8.5 seconds is inertia. No, it's approximately very similar to the real one, because for the Latvian power system, the inertia is around 10-12 seconds. Yes. So this one represents the turbine. Yes, for the turbine, you could see this block is closed because it is built specially to represent the turbine, how turbine operates. Yes, and this one is a valve, but this valve, of course, it's huge. You understand, it's a power plant. Yes, and to operate the valve, we need a motor. We give a signal to open more or to close. All the signal physical goes to electrical motor that opens and closes. So we have an electrical motor unit, yes, and every electrical motor has an inertia and time delay for response, as you understand. In this case, this unit represents this valve reaction, and it is how it's made. It's very similar, very simple. But what we're interesting, it's this TS. It's like constant. It's time constant, yes, for this block. And for now, it's 1 second. This block is very tricky because it is not existing in real life. It is here only to make the scheme more real. Yes. So this block does not represent any real object, yes, and real unit. It is artificial for the real life, but it is needed here to make this scheme more feasible, like the real life. And this one, it's the static coefficient. You could put it is in percent, yes, and it is here. As I said, it is about 3 to 7%, yeah, for different type of generators. So here we could see it's 5, yes. And for example, for our first test, let's make this different. Okay, let's make here 7, and let's make here 3. Yeah. Okay, so now we see that we have a reserve of power. Yeah, here is more than here, with the same deficit at time of 5 seconds. Let's see the difference of frequency. Here you could see, yeah. So the lower the frequency, so we have more power. We have increased, yes, the frequency, yeah, because we got more power, and this our, how to say, stabilized frequency here. And what is going on here? Yes, so we see the difference. Okay, let's use the same. Oh, sorry, this let's use, for example, 7. Okay, 7 is too much. Okay, let's put 5 as it is, and 5 for here as well. And here we have this deficit. Here it is 0.2. It means that we have 20% of deficit. Let's put here 10. And here when it appears at the time of 5 seconds. Okay, let's see the difference. Here we could see the same. Yeah, we have the same reserve power, but we have the difference in deficit. Yeah, and here it is the situation. Okay, so these are two schemes. Okay, sorry, I'll come back here to my Word document, and here we could see what here you could see the parameters. Yes. Okay.
Yes.
For yellow, deficit is this one. For blue, delta P here, and all other parameters. And here you could go to the screen. Yes. This is the first screen. The second screen, we have the difference in TJ for this inertia. I'll write this in there. Inertia for power system. As I said, inertia for power system is here. Yes, this unit represents the power system inertia. Okay, this one is yellow. Well, this one is yellow, and this is the blue one. Okay, this was okay. This first one, second one, third one is this load reaction difference D. The next one is about this static. Yes, 3 to 5. This is the valve.
Servo motor.
Valve motor. Yes, valve motor with its like constant. Yes, represents here. This one is E. What was I forgot. Okay, this one. Okay, this is okay. I need. Okay, wait. I forgot the word. Amplifiers. Yeah, it was an okay. This is just an this one is just an amplifier. So here you could see on
amplifier.
Yeah, giant only coefficient. Yeah, it represents only the of a giant block. So it's just an amplifier. Yes. How we amplify this reaction? Okay, and this is not very interesting, but okay, it's an amplifier. I think this is not useful for you. I can delete this one. With next one is this is for this. As I said, this is a little bit artificial, so I think this one we could skip as well. Okay, this is a scheme number 2 goes. Okay, let's page break. Okay, so this all for the first scheme. So okay, let's come back. So some different parameters, and you see the differences in the frequency. So your task is describe the impact and what you see. Yes, at the print screen. All these schemes you will get as well. Okay, this for the first one. Okay, we have scheme number 2. Okay. Okay, we have a scheme number 2. Scheme number 2 is very similar to the first one, but now we have two power generators, two hydropower generators, this one and this one, and they are connected. They got their inertia, and they are connected via a transmission line. Yes. I'll draw you what we, okay, so this is generator 1. This is generator number 2. This is transmission line, and here we got load 1, and here we got the load 2. What is the idea? For example, this generator can produce 100. This one can produce 50, yes? And this load consumes 50, and this load consumes 100. Yes? It means that we got a power flow 50 from here, 50 here, and 50 here. Yeah, I think it is clear. Okay, so in this case, this is transmission line, these two generators. And here we could see what is going on when we have a transmission line, because transmission line could be overloaded as well. For example, let's run. And here we could see at this block represents the same difference in power. Here we got the difference 0, and here we got different the deficit of 20%. So it means that in a normal regime, this system are in balance, yes, but something happened, any fault, and here we got at this bus. So we have a deficit at this bus of 20%. Or we got a deficit at this bus of 20%. And here we could see the reaction. Okay, I can. When this happened. And here we could see the reaction on these. These are frequencies, yes? Oh, sorry, misclicks. Here we measure frequency at bus 1 and at bus 2. So we measure, Paint, where are you? Okay, we measure frequency here and here, yes? Okay, frequency. And here we see that the frequency in the power system, when something happens, it's not similar. You see the difference in fluctuations. The same as it was, for example, in a blackout, in Italy blackout, as we discussed it, yes, due to all these issues that happened to Italy power system, yes, different generators stopped at the different time moments with different issues. That's why, because the difference in voltage and difference in this frequency was not the same for all the generators. And here is an example what is going on for the power network. Okay, for example, if we put here, okay, sorry, if we put here, this is a load, but this is a deficit. If we put, for example, the equal deficit, yes, of, oh, sorry, here we got the deficit of 0.1, 0.1, yeah. If all is symmetric, yeah, we will see the symmetric situation here, yes. But when we have an asymmetric system, yes, okay, we got deficit here, and nothing is going here. So it means that we got a deficit here, and so the power should go from here to here, yeah. And what is more, we could represent, for example, if we got here, oh, come here. less reserve than here. For example, we have here 7%, here we have 3%, and the deficit is here. So what will happen with frequency, yeah, at the different buses? Okay, here we could see these different fluctuations. Okay, so what we got for the scheme number 2? Okay, for this scheme number 2, we got only, okay, the first is when all the parameters are equal, we have difference in delta PS, so different deficit is only for the first one. The second scenario is when we have a different TJ, yep, different inertia for each generator, and here we could see the difference. The first scenario, we have different response for the valve. Yeah, okay. Motor. This is in it. Okay. And here we could go this different S for this static coefficient different reserve. And this is, I think, okay, fifth one, no. Okay, this one. Okay, this one we could delete for you. Okay. Okay. Static. Okay. Static. Static. You could delete. Okay. And this is okay. Scheme number 2, number 3. Okay. Scheme number 3. And this one was scheme number 2. Scheme number 2. This one was okay. Scheme number 3. Scheme number 3. And where it is, scheme number 3. Scheme number 3. Scheme number 3. The same as the first one, the only difference for the first scheme, this you don't have a transmission line. Okay, I will paint where you go. Where you go, so we have a generator. We have a transmission line and we have a load. This is L1. This is generator. And one more. This generator is with infinitive power. For the first scheme, this is infinitive power generator. So for the research, infinitive power generator. So, and here, just a scheme to test what will happen if we have an infinitive power generator. So we have enough power to deal with everything, yeah? And the main interesting thing is, yeah, the time, because here at the same scenario, at the time of 5 seconds, we have a deficit. Okay, let's see what is the deficit here. Okay, 20%, the same, 20%. And we have a power drop, we have a frequency drop here, we have an operation of regulator. We could see the overcompensation. Yes, we have an increase of frequency and stabilization. But you see the time at the beginning of the process 5 seconds, the end of the process is 10 seconds. So here we could see if we have enough power to deal with the troubles, yes. What is happening to the power system and what is the time to deal with the trouble, yeah? How long this frequency fluctuation will happen. And here we could test in this scheme, this process. And here for the scheme number 3, okay, where it is, scheme number 3. Okay, this is scheme number 3. Here we got different parameters, yes, and here we could see the difference in fluctuation. Okay, but this scheme number, okay, let's this one, scheme number 3. Here we go, the frequency. Okay, this one, I think. This one. This is for frequency, but this is for the load. For the load, I think it's not interesting. So second one is for the difference in statism. Okay, this for the valve. Okay, and this one we could delete. So, okay, so for the last scheme, the main thing what is interesting to test is, okay, let's come back here, is this. For example, if we have only 1% here, yes, this statism, yes. How long this process will happen, yeah. Okay, this statism, you could see now here, it's not like, no, it's not a real reserve power, yes. Because here is an infinitive power generator. For this scenario, this statism represents, how to say, how much power could we add for the one, how the time step, yes. Because for the real one, when we have a limited power, of course, this statism, yes, represent how much power could we regulate for each time step, but with the limited amount of power. But here we don't have these limits, that's why we see this oh, forgot the word, this frequency restoring of the frequency, yes, but here we got these fluctuations because we have this very small statism, and it means that we have very small regulation range, very small range for regulation. Okay, here we got, these are these three schemes, and we have one more scheme for you. Let's say, I think this one, not this one. Yeah, okay, I think yes, this one. Okay, this scheme for you. Okay, okay, this should go. Okay. Yes. Okay, what we got here? The same. Oops. Like it is in scheme number 1. Scheme number 1 is here, but here we got two types of generator for okay, CHPP and for the hydropower. Yeah. Here this gray one are pictures, yes, just how to say, to mark this block. I haven't used these pictures here, so here we got only the this, how to say, this scheme is just a copy paste. Yes, I don't have a link to these pictures because these pictures should be in a map. Yeah, oh, sorry, not this one, but like this one. Yeah, this picture should be in the same map. So here I don't have this link to the pictures. That's why I got these question marks. Yes, but it is not so important. In this way, we have our power system represented with two types of generators. You have CHPP and hydropower plants. Each one represents with its own. Here you could go for hydropower of static tism of 5. And here we got here the statisms of not this one. Okay, or yes, this one of 6, I think. Yes, coefficient transfer function 6. Yes, because here we go, and here we go. Yeah, a to 100, and here we go 5. Sorry, I just a little bit forgot. So it's a is equal to 5 number coefficients, and here we go. Okay, here, yes, here I don't got this is okay. Yes, all is correct. I just checked because this module, yes, maybe I'll explain. Here we put this in percent, 5% is here, yes, but the real one, these blocks is connected with a like a minus block, and this value that you're adding 5 is divided by 100. For this block, you don't, it is connected like it is, this minus is here, so it is okay. And here we got this 6%, so we don't have this diff function. This is 6%. Yes, so here we got 6%, here we got 5%. Yes, because hydropower plant is copy pasted, but the CHPP unit is a little bit different. Here you could see. And as I said, we have a limit power, yeah, for this regulator, because this is a saturation. So here we add a limit power. Here we go, this limit power, yes. So in this case, when we have a regulator, the statism, and a limit power limitation, yes, in this way, here we are saying, based on the static stride curve, the power reaction on the frequency deviation by each time step, and here we are adding a limit of power. So this scheme is more true, because previous scheme was more simple. This is more complicated and more true scheme. And as we say, the power system, no, it's quite complicated, almost impossible to represent only with one type of generator. That's why here we represent power network, concentrated power network, with two types of power generators, like a CHPP and hydropower. Okay, let it be. But what is the idea? The idea is to use this under frequency load shading automation, yes, to deal with this, as it is represented here at time step 10, the deficit of 25%. This is the power network. Here we could see this inertia. It's a 10% here. Yeah. Or 10 seconds, sorry, 10 seconds inertia, we in second here. Here we got the deficit. Oh, sorry, I just forgot. Here we got two step blocks. So time step 5 second deficit, and the second one at the time 10 seconds appears the second deficit. Yeah. And here we got this automation, this under frequency automation. Here it is. And here we got start frequency and the amount of load we are disconnecting. Why here we got two set points? Why use this block? Because it is very simple. It's because it's a model. Yeah, I'll explain. Okay, frequency. We have a frequency drop. And the frequency automation regulators, we have this increase. And not to let the one step of under frequency, this shading automation work for, okay, it goes down, yeah, to start here and again here, yes, because we only once can disconnect one load, yes, that's why we use this such type of saturation like this one, yes, block parameters, this relay. But the main idea is a start point when it starts, yes. Your task will be to find the best set points of frequency and for the load. Here we could see the load. If you sum all these numbers, you'll got the total amount of load connected to the under frequency automation. So your task will play with this scheme and try to find, yes, the best set points for each stage. Here we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stages for this under frequency automation. And here we got two types of deficit. Yeah, no, let's say we don't have the deficit more than, for example, okay, here we got, I think, 25 and 25. It's too much. Let's say that we don't have more than 40% of total deficit. Yes, this could happen, for example, for the first fault only, for example, 10%, for the second 30%. What is the idea? What we are trying to test here, as it is in an Italy blackout, yes, we have the first initial fault and the first deficit. But due to all these troubles with the lower frequency, we lost some generation as well. But here we are using not a generation loss, but we use an additional okay, sorry, it is an additional different generation loss. Yes, it is the same. Yes, so here we have a deficit, first initial deficit with for example, for any due to any fault, and here we got the secondary generation loss due to the low frequency. And here we could see how our automation could deal with this problem. So here, from here, we could see how much load we have disconnected. So here you could see we have disconnected 12%. No, okay, 13%. Yes, 13%. And here we got the total deficit of 25 plus 25 here. And what is going with frequency? And here we could see we have stabilized the frequency. Yeah, why? Because we have this response from the generator here, we have response from generator here, yes, additional power, and out of the low disconnection, and the frequency is stabilized, yeah, to the lower value than 50 hertz. Yeah, so your task is to play with this scheme and to find the best set points, because for example you could make set points, yeah, to restore the frequency using this under frequency 1 automation. Yes, because here we don't have this second under frequency automation, which task is to restore the frequency. Yes, this one is only to stop the frequency decrease. Yes, this first. So your task is to play with this scheme and to write, yeah, a report about the set points and about the scenarios. So
Okay, Professor.
yes. Okay, what do I need to do for you? I need to send you all these schemes. First of all, okay, let's make okay. Oh, I can't make error here.
But you can send to the Dropbox link.
Yeah, I can send to the Dropbox, but due to the all this, how to say, but it's quite stupid that I can make an error. I try to make, because it's a remote control, I try to make it here, for example, in MATLAB. Let's see. Okay, it's a lab. Okay. Okay. Yeah, from my PC I can make it. Okay, so first of all, I need to mm, okay, this one. Okay, the next one, what I need to add is this. So, okay, no, I need to save. First, I need to save. I need to save it for you. Okay, to close. And okay, let's. Okay. Wait. I don't like this type of adding. I like more the attachment. Let it be like an attached. Okay, this is, and I need to add this. Okay, and this one is how it calls previous 25. Okay, 25%. And it is somewhere in my documents. My documents. It is. I forgot which is image. It is MLX. The MDL, yeah, it's MDL file. Okay, not because these schemes are really old. New schemes could have different. Okay. SLX. Okay, yes, it's an SLX. SLX. And this is this one. Okay. Okay, so let's recap. What should you do? Send for you. Okay, here you got the screenshots and the schemes. So you should comment each screen, yes, with this parameter. So what is the impact of the each parameter, what you see as a figure, yes? So you should describe the impact of each parameter on each block, yeah, for each screen. So this is quite similar. And for this one, you should play with the scheme to find the best outer frequency automatic set points. So set points are the start frequency and the load, no, the demand, yes, the power of disconnecting load. Here in the percents, 7%, 5%, 1%, 25%
Yeah.
here. So this is
Okay, I have one.
the same as here. Here we got the deficit at time of 10 seconds. Here we got deficit of 25%. But as I said, let's make that the total deficit for these two how to say serious faults, yes, not more than 40%.
Okay.
Let's limit it. And here you could use, for example, play with this limit saturation, for example. But as I said, it's to this limit is t from 3 to 7%. So here we got the 5%, yes, represented here. So it's not so actual. Let it be. It could be 5% for each type. So it means that, you see, for example, for this scheme, they are equal and they are 5%. It means that the 50% of power generation, power network is from CHPPs, and 50% are from hydropower plants. Because this saturation limits, yes, how much power based on the total, no, versus the total power we could get from each type of concentrated generator. For example, if we have only 10% of hydropower plants, yes, and 90% of CHPPs, it means that here, yeah, we could, how to say, generate, for example, 10% more, but 10% from 10%, it means that it will be only 11% to all the power generation. Is it clear?
I have one doubt. How can I check the result through the graph?
Okay, yes, it's here you have two scopes. Yes,
Okay.
this one here, because this is the base frequency. Yes.
Yeah.
Oh, sorry, this is the base frequency, and this one is a frequency deviation due to all what is going here. So from here we could see what is going with frequency.
Yeah.
And here we could see what is the under frequency automation, how to say, operation result. Here we could see the steps. First step, second step, third step.
So,
Here we got the 1, 2, 3, 4. 4 stages of under frequency automation have disconnected their loads. Yes. And this is a total amount of disconnected load, number of stages and the total amount of load. So here we got two scopes.
but in the EAFF underscore 1, I need to
Yes.
change the frequency for 7 stage.
Here
8 stages.
here you could change for each stage start frequency and the power of load. You have only two parameters for each stage that you could change.
Okay.
Here.
I can enter number, or can you repeat for one parameter?
Yeah, for example, this is a giant. Yeah, this represents the power. Now it's 7%.
Okay.
If you put here 1, means it will be 1% only. And here, for this iteration, no, okay, it's a switch. Yes, switch on, switch off. But we're interested in this. You see, output then on, output then off. So it is this one. This one, I think, represents the start frequency. Let's see. Okay, just to be correct. Let's see, here we got the frequency. So it started at 49.2. Yeah, it means that sorry, here it means that 49.2. Okay, we have a time delay. What is time delay? It's no 0.5 seconds. Okay, let's put the delay 0, and to be correct, let's Let's run once more to be correct. Okay. It's paused. Okay, sorry, continuous. Okay, ready. Okay, so yes, I think what is it? I understood, yeah. When we disconnect, I see. Sorry. Okay, if I want to check, I need to make such, because we are disconnecting, but it means that the speed of frequency drop changes. Yeah, it's the start point is 49.4. So it means that 49, this one, the upper one, is a start set point. So this one, the upper, oh, sorry, what is upper? The lower one is a start set point. Because let's put this delay like this. So yes, the lowest one is the start set point. Here we could see the frequency. Here we got the result of operation. Yeah. No, okay, it was only one stage because 50% of load was connected to the first stage. We have two deficits, the first time moment and the second time moment. Here we got this statism. Here we got this inertia of the power system of 10%. And here we have this limitation, this reserve of power for each type of generator, based on the, how to say, based on the how this power is separated between two types of generator. For this scheme, with this saturation, it means that the 50% of generator are CHPPs and 50% of generation are from hydropower plants. Maybe I could try to explain once more. So this is a whole power system. If we have only 10% of CHPPs, yes, no, 10% of the total generation, and the reserve is 10%, so it means that the 10% from 10%, it means that we could increase, yes, the total generation of hydro from 10% of total to 11%, because we have a reserve only 10% from 10%. That's how it is divided into two types. For now, it is, how to say, it is 50-50. But you could not use these parameters. You could leave it like it is. Okay, if you will have any questions, just write me an email and I'll try to help you.
Yeah, sure, Professor.
Okay,
Did
for
you
today
check?
it is all.
Did you check my last